Welcome back. Now we're going to do an example problem from section 2.1 with the separable method. We'll start with the exercise number 5, where we're trying to determine if we can, and then if we can, solve x prime equals x over t. Okay, so first we check. Can we separate that into a product of a function of t times a function of x? Yeah, it's a division, so it's easy to separate into a product. Check. Got a straight one there. Perfect. Okay, so now we then separate and integrate. So first, we bring all the x terms on the left, all the t terms on the right, and then we integrate. So I'm going to pull that out as a 1 over x dx and a 1 over t dt. Okay, so looks like we have the same kind of integration on both sides. That's pretty straightforward. So we get a log of absolute value of x on the left-hand side plus c1, log of absolute value of t plus c2 on the other side. And then we can do a couple of things. First thing I'm going to do is combine the constants, the arbitrary constants together. So we have log of x is equal to log of absolute value of t plus a new arbitrary constant. We'll call it c3. And then we'll exponentiate both sides. When we do that, on the left-hand side, we're left with the absolute value of x. On the right-hand side, we're left with a sum in the exponent, which breaks down into two exponentials. We first exponentiate the log of absolute value of t, and exponentiating the log cancels, leaving us with whatever is left inside the log. So we have the absolute value of t times e to the c3, like that. Now, c3 is an arbitrary constant, so exponentiating an arbitrary constant is an arbitrary constant, but it's positive, because exponentials cannot be negative or 0. So we then resolve it further by saying, well, absolute value of x is either equal to positive x or negative x. So let's push that plus or minus uncertainty onto the right-hand side. So we have x equals plus or minus. Now, since e to the c3 is an arbitrary constant, let's push that first. E to the c3 times the absolute value of t. Now, absolute value of t is, again, either plus or minus t. So we have a plus or minus t, a plus or minus x. Now, you would think that they cancel. They don't exactly cancel. You get plus or minus, you still have that same uncertainty. So we're going to bring all of that uncertainty into the constant. So now, even though x e to the c3 has to be positive, because we have the uncertainty of the sign, we get positive or negative. So I'm going to write this as x of t equals c, our final constant, times t. So there's our answer. Now, one thing you might have noticed is that e to the c3, even with a plus or minus, is not truly arbitrary. It cannot take every single value. There's one value in particular it cannot be, and that is 0. However, this new c can be 0. Let's check. How is that possible? So, if we let c equal 0, that means that x of t equals 0. And that means that dx dt, well, it's 0, take derivative, is 0. Well, dx dt should be equal to 1 over t times x. 1 over t times x, which is 0. That's true. So when x equals 0, it satisfies the differential equation, which means it's part of the solution. So we don't have to make any conditions on that c. It's truly arbitrary. And that wraps it up. So why does that happen? Well, our separable method assumes that we will divide by this function of x. And when we divide by it, we create some mathematical inconsistencies. For example, when x equals 0, this equation is no longer satisfied, even though the first equation is. So that's one thing we have to keep in mind, is that the math we do makes some assumptions along the way. When we divide quantities on both sides, we're making assumptions. Dividing here by x, assume that x was not 0. If x equals 0, then we couldn't. So we do need to check to make sure we're not excluding certain components of the solution, and checking to see if there are actually restrictions on the constant. For the most part, this method will create excessive conditions on the constants, and we can check to see which of those conditions are actually valid. Okay, on to the next one.